In this video tutorial, we will continue our review of grades 9 and 10 chemistry. In particular, we will focus on introducing the periodic table, Bohr-Rutherford diagrams, and ions and isotopes. The periodic table contains a lot of information inside of it. Every element has its own unique symbol made up of one or two letters. Now, most of the time these symbols will match up with their English names, so O for oxygen, N for nitrogen. But some elements do not have symbols that match up with their English names. So for instance, Fe is iron. Ag is silver. Elements that we have known about for thousands of years are assigned symbols that are based off of their Latin names. So iron, for instance, we've known about for a long time. Its Latin name was ferrum. That's where the Fe comes from. Silver as well, we've known for a long time, and its Latin name was argentum, which is where the Ag comes from. Meanwhile, elements that were more recently discovered are assigned symbols that are matched up with their English names. So for instance, oxygen was only discovered about 250 years ago. That doesn't mean that oxygen didn't exist back then. It meant that we didn't know about it. There are two major numbers associated with every element. The first is called the mass number, and the second is known as the atomic number. To help me remember this, I think of mass as massive, so whichever number is bigger is the massive number or the mass number, whereas the smaller number is the atomic number because atoms are small. So, small number, atomic number. Massive number, larger one, is the mass number. Now the atomic number also represents the number of protons in that atom. So for instance over here, chlorine has an atomic number of 17. Therefore, it has 17 protons. The atomic number also represents the number of electrons in a neutrally charged atom. So in this case, chlorine with the atomic number 17 also has. To determine the number of neutrons in an atom, we take the mass number and subtract the atomic number. So in this case, 35 minus 17 equals 18 neutrons. Please keep in mind that the mass numbers won't always be whole numbers. More often than not, they will have decimals. In those cases, you'll have to round to the nearest whole number. So for chlorine, 35.45 rounds down to a 35. While 39.95 would be rounded to a 40, 32.07 would be rounded to a 32. Now the mass number is measured in atomic mass units, and the symbol is a U. This was done because atoms are extremely small, and we can't measure them in units like grams or kilograms. Otherwise, it'd be something like 0.00000000000000000000001 gram, and that's just not practical. So instead, scientists made up a brand new unit called the atomic mass unit. As I mentioned before, the official symbol is a U. However, I will quite often use the term AMU to avoid confusion. In any case, one atomic mass unit is defined as the mass of 1/12 of a carbon-12 atom. This works out so that the mass of a proton or a neutron is approximately one atomic mass unit. So if the mass of chlorine is approximately 35 AMU, and we have 17 protons, each one worth about 1 AMU, then 35 AMUs minus 17 AMUs leaves you with 18 AMUs, and since each neutron is approximately one of those, there are 18 neutrons in total for chlorine. We generally don't worry about the mass of electrons because they are very small in comparison to the mass of protons and neutrons, approximately 1/2000th of an atomic mass unit. So when you look at the mass number, you're really only talking about neutrons and protons. In grade 9, you learned about Bohr-Rutherford diagrams and how they can be used to represent atoms. So let's briefly review over this. Fluorine has a mass number of 19 and an atomic number of 9. You'll notice that on this sheet, the mass number is on top and the atomic number is at the bottom, but it's switched on most periodic tables. This is known as standard atomic notation, where the mass number must be at the top and the atomic number must be at the bottom. Just remember that the bigger number, the massive number, is the mass number, and the atomic number is the smaller one, and that should help you avoid confusion. Alright, so the atomic number again tells us the number of protons, as well as the number of electrons in a neutral atom of fluorine. So it has 9 protons and 9 electrons. To calculate the number of neutrons, we subtract the atomic number from the mass number, and that gives us 10 neutrons. Alright, so protons and neutrons exist inside the nucleus. So this little circle represents the nucleus. Meanwhile, electrons orbit around the nucleus. So the first shell can hold a maximum of 2 electrons. I like to put these electrons paired up together because, well, electrons tend to pair up inside the atom. But some textbooks like to draw the electrons on opposite ends. So either of these two methods is fine. But I'll just stick to what I usually do for now. Now when it comes to drawing electrons, the rules are 2 electrons can fit in the first shell, while 8 electrons can fit in every other shell after that. Now, just so you know, this last part is not true. We do simplify things in grades 9, 10, and 11, so you can live with this for now. But if you plan on taking grade 12 chemistry, you'll find out why this last part is not correct, as the third shell actually holds 18 electrons, while the fourth shell holds 32. But for now, let's just live the lie and pretend first shell holds 2 electrons and every other shell after that holds 8 maximum. So I've drawn 2 electrons. I need to draw 9 in total, and there's no more room in the first shell, so I need to draw the second shell. Now, when it comes to the layout of electrons in the second shell and above that, I do care about where you put them. So what we're going to do is we're going to start in the north and draw our first electron up here. Then we're going to move to the east and draw our next electron here. Move down to the south to draw our next electron, and then move to the west to draw another. So far we've got 6 electrons, but we need to draw 9. So at this point we're forced to double up, so we're going to double up and pair them, partner them together. Okay? 8 and 9 electrons drawn in total. Alright, now if you had more electrons that you needed to draw, you would fill in this last spot over here, but because this shell can only hold 8 electrons maximum, you would simply draw a third shell and start filling it out north, east, south, west, and then doubling it up north, east, south, west, and continuing on. But fluorine only needs 9 electrons, which we've drawn, so we're good to go. Now it's very important that you draw these electrons in an organized manner. If you give me something like this, I will deduct marks. First, it's very difficult for me to count the number of electrons you've drawn in together, especially if they're all crowded together. But second of all, leaving the electrons spaced out like this helps us to visualize how chemical bonds will form, how the atoms will attach to one another. While this is just a jumbled mess. Alright, so what I'd like you to do now is press pause and then try and draw the Bohr-Rutherford diagrams for all the other elements you see over here. When you're done, press play and we'll take it up together. Alright, so your Bohr-Rutherford diagram should look something like this. Please check your work and make any necessary corrections. There are many different versions and layouts for the periodic table. However, this is the most common version that's used for introductory chemistry. Initially developed by Dmitry Mendeleev, it organizes the elements based on their atomic numbers. But that's not the only pattern we can find on the periodic table. If we draw a staircase on the periodic table, elements that touch one full side of the staircase are called metalloids. Now, they must touch one full side of the staircase. Corners don't count. Alright, so only the sides. The exception, of course, is this guy over here, which is aluminum. And of course, aluminum we know is a metal, not a metalloid. So to the left of the staircase are the metals. Again, there's another exception up here. Hydrogen is definitely not a metal, so we call it a non-metal. So with the exception of hydrogen, these non-metals are generally found on the right side of the staircase. Now you notice there is a gap over here. That's where this whole block of elements normally fits in. So the periodic table should look something like this, but in order for this to fit on a page properly, they decided to take this block of elements out and then slam these two sides together. Again, just so it fits nicer on a regular 8.5 by 11 sheet of paper. Alright, so just keep in mind that technically this block belongs in here. Now these two groups over here, I like to call them the mountains if you will. The two mountains on either side are called the representative elements because these elements represent the patterns of the periodic table very, very well. While these guys over here are called the transition metals. They do have a pattern, but it's not as obvious, it's not as pronounced as the patterns you will see later on with the representative elements on either side. And finally, these guys over here are called the inner transition metals. Now on the periodic table, we no longer call these columns. Instead, you're going to call them groups or families. And they are numbered groups 1, groups 2, groups 3, all the way up to group 18. Now some of the older textbooks may number them as groups 1A, group 2A. Now I'm going to ignore this part. This is the B block. They don't really follow the pattern, as you can see. So that's why these are the representative elements, because they represent the patterns of the periodic table very well. Versus over here, the transition metals, their patterns aren't as obvious. So I'm going to skip the B block. Then go straight to 3A, 4A, group 5A, 6A, 7A, and last group 8A. Now the reason why I'm including the old numbering system is because it will help us later on in identifying another pattern on the periodic table. Alright, now instead of calling these rows on the periodic table, you're going to call them periods. So this would be period number 1, period number 2, period number 3, period number 4, all the way up to period number 7. Now if you recall, these inner transition metals belong in this gap over here, so this would still be period number 6, and this one would be period number 7. Now why do we refer to these columns as families? Well, let's pretend I'm walking down the street. I'm walking down the street and I see two people who I've never met before. Even though these people are complete strangers to me, I can still say, oh, I think they are from the same family. How can I do that? How can I make that statement if I've never met these people before? Well, it's probably because they look the same, or they have similar features between them. Well, if I look carefully at my Bohr-Rutherford diagram, let's take a look at this family over here. What is the one feature that all of these elements, beryllium, magnesium, and calcium, have in common with each other that make them part of the same family? They all have the same number of valence electrons, so the same number of electrons in the outermost shell. Take a look at it. Beryllium has 2 electrons in the outermost shell. Magnesium also has only 2 electrons in the outermost shell, and same with calcium. If we look at the group 1 elements, they all have 1 valence electron in their outermost shell. Take a look at boron and aluminum. In group 13, otherwise known as group 3A, they have 3 valence electrons. So that's why I included the old numbering system. 1A elements, group 1A elements, they all have 1 valence electron. Group 2A elements, they all have 2 valence electrons. When you get over here, group 13, otherwise known as group 3A, they all have 3 valence electrons. 4 valence electrons, 5 valence electrons, and so on and so forth. Now, if you forget this old numbering system with a 3A, just look at the last digit in the group number. That also tells you the number of valence electrons in that particular group. So the group 1 or 1A elements all have 1 valence electron. The group 2 or 2A elements all have 2 valence electrons. Group 13 or the 3A elements all have 3 valence electrons, and so on and so forth. The pattern continues on. That's why we call these the representative elements, because they represent the pattern very well. The only exception over here is group 18 or 8A. These guys all have 8 valence electrons in their outer shell, but helium does not, because it maxes out at 2 electrons in the first shell. The first shell cannot hold any more than 2 electrons, so it can't actually have 8. So as you move from left to right, we start to increase the number of valence electrons in the outer shell. With numbers in the same group having the same number of valence electrons, thus they are called families. Once again, looking at the Bohr-Rutherford diagrams, you should be able to see another pattern popping up. Take a look at period 1. They all have 1 electron shell. If you look at period 2, all these elements have 2 electron shells. If you look at period 3, every single one of them has 3 electron shells. And when you get to period 4, well, they all have 4 electron shells. So while the group number tells you how many valence electrons are in that element, the period number tells you how many electron orbitals or electron shells are present in that atom. So as we go down the periodic table, we increase the number of electron shells in that atom. Period 1, 1 shell. Period 2, 2 shells. Period 3, 3 shells, and so on and so forth. So tell me, how many valence electrons are in this element? Because it's in group 14 or 4A, it has 4 valence electrons. But how many electron shells does it have? Because it's in period 4, it should have 4 electron shells. Well, what about this one over here? How many electron shells does it have? Because it's in period 6, it should have 6 electron shells. Well, how many valence electrons does it have? How many electrons are in the algebral shell? Because it's in group 2 or 2a, it should have 2 valence electrons. So just by looking at the position where that element is found on the periodic table, you should be able to make predictions about the number of valence electrons and the number of shells present in that atom. Of course, this pattern works best for the representative elements, not so much for the transitional elements. Now, these are just some of the patterns we will see on the periodic table. There are so many more. And that's one of the reasons why we like to organize things in science. If you organize things, if you organize your data, you might be able to see a pattern. And if you see a pattern, you might be able to make a prediction. In fact, when Dmitri Mendeleev began to organize the periodic table, he noticed that there were gaps, elements were missing in the pattern. But based on their position in the periodic table, he was able to predict what properties and characteristics these elements would have. And of course, within 15 years, all 3 of these elements were discovered, and they were exactly as he predicted them to be. So remember, if you organize your data, you may be able to find a pattern. If you find a pattern, you might be able to make predictions. And if your predictions are correct, you might be able to exploit them, and that's where science turns into technology. Alright, so let's go back to focusing on the subatomic particles that make up the atom itself. So, what happens if the number of protons change in an atom? Let's take a look at gold. Gold has an atomic number of 79, meaning it has 79 protons. Well, what happens if I slam another proton into gold? Now it would have 80 protons. But who else also has 80 protons? Mercury. You will notice that every single element on the periodic table has a unique atomic number, a unique number of protons. No 2 elements have the same identical number of protons. So based on your everyday experiences, how often do you see gold turning into mercury? The answer should be never, unless you've been ripped off. So based on that knowledge, it is very rare in our everyday lives for atoms to lose or gain protons. The only time that occurs is during nuclear reactions, not chemical or physical changes. So, since the atomic number is unique to each element, and the atomic number represents the number of protons in that element, changing the number of protons changes the element identity. Furthermore, if you change the number of protons, because protons have mass and charge, you will also change the mass and charge of the atom itself. Alright, so what happens if you change the number of electrons then? Well, this would affect the atom's charge, but not its mass. All right, the mass change is very negligible. So negligible means it's so very small that you don't really have to worry about it. If you recall, the mass of an electron is approximately 1/2000th of an atomic mass unit, while the mass of a proton or a neutron is approximately 1 atomic mass unit. You would have to gain or lose 2,000 electrons in order to equal the same mass change as if you had lost 1 proton or a neutron. That would be like trying to lose weight by getting a haircut. I mean, yeah, technically you're losing the mass of your hair, but the mass of your hair is typically negligible in comparison to the mass of the rest of your body. Anyway, just remember that changing the number of electrons will affect the atom's charge, but not really its mass. Now, a charged atom is called an ion. Let's take a look at this lithium atom over here. If lithium loses its outer valence electron, then this outer shell over here disappears. Because it has lost this electron, and an electron is a negative particle, by losing a negative particle, you become more positive. We now refer to this as a lithium cation. And a cation is a positive ion. Now, to show that this is not the original lithium atom, that it has changed from the original, we put square brackets around it to show that it's an ion. You must also indicate the charge of this ion, since it's lost 1 electron, there's the number 1, and by losing a negative particle, you're more positive, that's where the positive charge comes in. Now be careful, don't write it as a +1, you must write it as a 1+. 1+ refers to its valence charge, while +1 refers to its oxidation number, and that's something we'll learn about in grade 12 chemistry. So these are 2 different things. Don't use this symbol, use this one, where the charge is behind the number 1. Now, In the case of fluorine, if it gains an electron, it will become more negative, because remember, electrons are negative, so if you gain a negative particle, you become more negative. Since the fluorine gained one extra negative particle, its valence charge is a 1 minus. Again, don't forget to put the charge behind the number 1. We also put square brackets around it to show that it's no longer the original fluorine atom, but now it's a charged ion. In this case, because it's a negatively charged ion, we say it's a fluorine anion, where anion means negative ion. So remember, cation, positive ion, anion, negative ion. I memorize this because the T looks like a positive symbol. Now you may have noticed I used X's and dots to represent electrons. The reason why I used X's and dots is to help me differentiate which electrons originally belonged in the fluorine and which ones were added on after the fact. Alright, so the last one we need to worry about is what happens when the number of neutrons change. Doing so will affect the mass, but not the charge. So remember, neutrons have a mass of approximately 1 atomic mass unit, but they are neutrally charged, so they'll affect the mass, but not the charge of the atom. Since the number of protons remains unchanged, it is still considered to be the same element name. However, elements that differ only in their mass are called isotopes. These are the 3 naturally occurring isotopes of hydrogen. You'll notice that their symbol and atomic number are identical in all 3 cases. As such, all 3 of them have the same number of protons, in this case 1. However, you'll notice that their mass numbers are different. Protium has a mass number of 1, deuterium 2, and tritium is 3. Remember that the mass of an electron is negligible in comparison to the mass of protons and neutrons, so therefore this mass change, if it's not the proton, it must be due to the neutrons. To calculate the number of neutrons, we take the mass number and subtract the atomic number. So 1 minus 1 is 0. 2 minus 1 is a 1. 3 minus 1 is a 2. So tritium has 2 neutrons, which makes it the heaviest one. Deuterium only has 1, while protium has 0. Again, protons and neutrons have a mass of approximately 1 atomic mass unit. So 1 plus 0 equals to 1 atomic mass unit. 1 plus 1, 2 atomic mass units. And 1 plus 2 is 3 atomic mass units. Even though all 3 are considered to be hydrogen atoms, because of their different mass values, they will have different physical and chemical properties. With protium, its percent abundance on Earth is 99.998%, meaning 99.998% of the Earth's hydrogen is going to be in this form, protium, with only 1 proton and 0 neutrons. So this is considered to be regular hydrogen on Earth. But if you go to a different planet, these percent abundance values will change. Looking at deuterium, its percent abundance on Earth is approximately 0.0018%, so it's pretty rare in comparison to protium. Deuterium can be used in heavy water, which we use in Canadian nuclear reactors in order to control the nuclear reaction because it's very good at slowing down neutrons. Meanwhile, tritium's percent abundance on Earth is 0.0002%, so it's the rarest of the naturally occurring hydrogen isotopes. Well, at least on Earth. It is also radioactive. So, as you can see, by changing the mass values, you don't change the element identity, but you do change its properties, and thus we call them isotopes, elements that are different only by their mass values. Now, with all these different isotopes, how does the periodic table arrive at this atomic mass to represent all 3 of them, 1.11 atomic mass units? You can't just pick 1 atomic mass unit to represent all 3 isotopes, so what we do is we average them. But we can't just do an average mass calculation where we just take the 1 atomic mass unit, 2 atomic mass unit, 3 atomic mass unit, and then divide it by all 3, because if you do that, you get a value of 2 atomic mass units. Meanwhile, the periodic table is quite clear that it's not 2 atomic mass units, it's 1.01. Instead, this average mass must be based upon percent abundance. It has to factor in how commonplace each of these isotopes is on Earth. Imagine if I had 4 family members. 3 of us weigh 75 kilograms, but 1 person unfortunately is morbidly obese at 400 kilograms. Well, if someone asked what is the average mass for your family, it would be 156 kilograms. That is unhealthy. The doctor would want to put all of us on a diet when really it's just 1 person that needs to be on a diet. So using a regular average calculation can be misleading, like in this case over here. These three masses are not equal. Most of the world's hydrogen is going to be protium with a mass value of 1. Very few of it is 2 and 3. That's why the average atomic mass for hydrogen on the periodic table is a 1.01, to show that most of the world's hydrogen is going to be a 1, but there are some heavier isotopes of hydrogen, but they don't make up too much of the world's hydrogen supply, so we say 0.01 to show that they exist, they are just not very commonplace. Alright, so how do we do a proper average calculation then? You would take the percent abundance of the first isotope multiplied by the mass of that first isotope. Then add that to the percent abundance of the second isotope multiplied by the mass of the second isotope. Then add that to the percent abundance of the third isotope times the mass of the third isotope, and so on and so forth for however many isotopes exist for that particular element. Alright, so let's take a look at this example over here. I have boron 10. Now be aware, instead of writing it in this format, textbooks may call it boron-10 or B-10, while this one, instead of written here, might be written as boron-11 or B11, and that's one way to differentiate between these two isotopes of boron. There is no need to mention the atomic number of 5, because if it's boron, the atomic number must be 5. That number cannot change. But its mass can change depending on the isotope. Anyway, boron-10 has a 19.78% abundance and a mass value of 10.01 atomic mass units, while boron-11 has an 80.22% abundance and a mass number of 11.01 atomic mass units. So I'm going to plug these values into the equation here, and I'll end up with this. Now here is a common mistake students will make. You cannot leave these percentages as a percent. You must convert them first into a decimal value. Remember, the word percent means out of 100. So percent per 100. Cent is the prefix we use for century, which is 100 years. So percent for every 100. So when we say 19.78% or 80.22%, we're actually saying 19.78 out of 100% and 80.22 out of 100%. And when you divide 19.78 by 100, you get 0.1978. When you divide 80.22 by 100, you get 0.8022. Think about it this way. If you got 7 out of 10 on a quiz, what was your percent? Well, if I punch this in the calculator, 7 divided by 10, I would get 0.70. So does that mean I earned 0.70 on a test? The percentage was 0.70%? No, we would have to multiply by 100% to turn this into a 70%. Alright, so when converting a percentage into a decimal, we divide by 100. If you're converting a decimal into a percentage, we multiply by 100. So in this case over here, we must convert these percentages into decimal values before we can continue on with our calculations. So continuing on with our calculations, we get a final value of 10.81 U is the average atomic mass based on the percent abundance values we see above. Since most of the boron on Earth is boron-11, 80.22% of it is boron-11, that's why this average is closer to 11 than it is to a number 10, because only 19.78% of the world's boron is boron-10. So this average over here, 10.81, is much closer to 11 than it is to 10. So just by looking at the average atomic mass values for each element on the periodic table, I can guess which isotope of that element is most popular, most commonplace, most abundant on Earth. Let's take a look at iron, for instance. Which isotope of iron, iron 54, iron 55, or iron 56, do you think is most abundant on Earth? Well, look at the mass number. It's 55.85. This 55.85, if I had to round it to the nearest whole number, would be 56. It's much closer to 56 than it is to 55 or 54. If it makes it easier for you to visualize, think of it as $55.85. Let's say I had no change, I had to round it to the nearest dollar. Would I be paying $55 or would I be paying $56? Alright, so 55.85 is much closer to 56. So iron 56 is the most abundant isotope of iron on Earth. So let's do one last one. Silicon. Which of these 4 isotopes of silicon, silicon 26, silicon 27, silicon 28, or silicon 29, do you think is most abundant on Earth? Just by looking at its average atomic mass, we can see that silicon 28 is most abundant on Earth because 28.09, if you round to the nearest whole number, would be the closest value we have. Alright, so let's try a slightly different version of this question. Instead of trying to calculate the average atomic mass, I want you to calculate the percent abundance values. So now I've given you the average atomic mass, but I want you to find out what is the percent abundance for boron-10 and what is the percent abundance for boron-11. Now, a common mistake students will make when trying to solve this question is they'll say let X represent the percent abundance for the boron-10 and let Y represent the percent abundance for boron-11. But when you plug these variables into the equation, you can't actually solve it because now you have two unknowns but only one equation. So instead of using the variables X and Y to solve it, you should instead use X and 1 minus X. Think about it this way. If X is the percent of boron-10, then the remaining portion must be 100% the total minus whatever X is. That's what the remaining portion would be. Now we only have to worry about the one variable, X, instead of two variables, X and Y. And now we are able to solve for this equation. But why am I using 1 minus X? Shouldn't it be 100% minus X? Remember, percent means out of 100. So 100% divided by 100 is equal to 1. And that's where the 1 minus X comes from. Alright, so I'm going to start by expanding my variables. So 10.01 times the X equals 10.01X. 11.01 times 1 equals 11.01. 11.01 times negative X gives me negative 11.01X. I'm going to now rearrange and collect some like terms, giving me negative 0.20 equals to negative X. Therefore, X is equal to 0.20. But since we're looking for percentages, I need to convert this decimal back into a percent. Instead of dividing by 100, giving me 20% of boron-10. So boron-10's percent abundance is 20%. So the remaining must be 100% minus the 20% to give me the rest, which is 80%. Alright, so 80% boron-11. Now, unfortunately, your textbook only has the easy isotopic abundance calculation questions, so the ones where they give you the percent and the mass and you have to calculate the average. They don't give you the ones where they ask you to calculate the percent abundance. These questions can be found in the old textbook, page 170. So if you want more practice with these types of questions, please go to the old textbook, page 170. This concludes our lesson. Our next topic will be on trends of the periodic table and types of chemical bonds.